So, what we have told in the last lecture was the following, that is what we want to prove today, that if x bar is a local minimum of MP, the math programming problem, with inequality constraints only, then the following system this system, so there is m plus 1 inequalities, this system cannot have a solution D in Rn. Now, how do we prove this fact? So, I will just go to the board proving this fact. So, on the contrary, this is proved by contradiction, a standard technique in mathematics. So, on the contrary, I assume that D, there exists D element of Rn which solves the system. Which solves the system. System is the system 1, this particular system which I have written down. So, it solves this system, and now, so what we have is the following. Now, consider lambda strictly greater than 0, then take Gi x bar plus lambda d for any d, and then write down the Taylor's expansion. So, you are expanding a Taylor series around x bar, and then the error term. Actually, it should be O of lambda norm d, and that can be replaced by O of lambda, that is O of lambda norm d is same is an O lambda quantity. So, just a little bit of analysis you need to do to show that they are this a small O lambda norm d quantity is same as a small O lambda quantity. So, show this fact as a homework. So, as a little practice of basic analytical using analytical tools. Now, what I do is here I break up as 1 minus lambda Gi x bar plus lambda times Gi x bar plus grad Gi Now, since x bar is a solution to the problem and Gi x bar is less than or equal to 0 for all I, this is for each I, for each I this is true. So, Gi x bar is less than or equal to 0. So, 1 minus lambda, so if lambda is greater than 0 and lambda is sufficiently less than 1, when something is very less than 1, you make this sign. So, when lambda is very much less than 1, that is very near 0, then it implies that 1 minus lambda g I x bar is less than equal to 0, because this becomes non-negative or positive basically. So, what I have from here is the following. I have from this equation I am writing this. So, actually this whole thing now, because this is less than equal to 0, this thing is now less than this part. So, I can now divide by lambda to write now, because D is a solution to the system, this part is strictly less than 0, this whole part is strictly less than 0. Now, I can choose lambda as small as I like. So, this part is now, because O lambda by lambda, since O lambda by lambda is going to 0, which means that I can, as I choose lambda smaller and smaller, this quantity is vanishing, it is coming towards 0. Of course, this quantity could be negative, positive, whatever, in whichever way it is approaching, could be on from the negative side, could be from the positive side, it is approaching 0, it is in a neighborhood of 0. So, what happens, even this is positive, say, it becomes so small as I make lambda very, very small, that this is a fixed negative quantity, that the overall sum becomes negative. For example, this is minus 1, and this finally I make it so small that it becomes say 1/3 or 1/4, something like that. Then minus 1 plus 1/4 would become minus 3/4. So, for lambda greater than 0 and sufficiently small, you have g I x bar plus lambda d. Now, how you will, because for every I the lambda choice would be different. So, choose so there will be a threshold of lambda, there will be a lambda beyond whose after, for any lambda below that value, for a particular I, this would be true. So, for each I there would be such a threshold lambda, choose the one which is minimum and do it. This is a standard sort of argument that you make in real analysis, and so I expect the students to have some idea about real analysis, in the sense that they should be able to make this sort of arguments. Unfortunately, I would again like to stress, because this is a sort of a public lecture, and so I would like to stress on one fact, that this is a course on mathematical optimization, and this is not just a course where you are talking about some modeling, some problems and their softwares. So, that course is better possibly delivered by someone who is in the forefront of applications, especially from the departments of management and or for maybe from the engineering departments. So, I would like to apologize, and I would like to ask for the viewers' pardon that I am using mathematics which possibly is not of your liking, but I cannot help. Optimization is a mathematical subject. I am not doing any more involved stuff like calculus or variations or any other thing like infinite dimensional optimization. I am just remaining in optimization with derivatives, but mathematics is the involved stuff, and optimization is a mathematically involved stuff, and you really have to go through these things. Those who are from the engineering background, I am sorry that this is essentially a course in mathematical optimization. It is the foundations of optimization, and the foundations of optimization is based on heavy mathematics, because it is a mathematical subject. But there are a lot of insights which we will start giving once we establish the so called Fridge-on multiplier condition or Fridge-on necessary condition. So, this is true for all I equal to 1 to m. This implies that x bar plus lambda d means gi x bar lambda d is strictly less than 0 is feasible Now, once I know this, then let me go to the first part of the thing. The first part is, so D, because it is a solution, also solves this. So, which means now I can write because D is a element which is solving this system. Now, again we will take the help of the Taylor's expansion around x bar, sorry there is no Fi, it is only F. Have I written Fi? Sorry, there is no Fi, I made a mistake, it is only F, there is no because there is only one objective. So, now f of x bar plus lambda d is equal to f of x bar plus grad f x bar lambda d plus o lambda, small o lambda. So, this means now that f of x bar plus lambda d minus f of x bar by lambda is equal to grad of f x bar d plus o lambda by lambda. Now, this is strictly less than 0. Again by a similar sort of argument as before, so we can conclude for lambda greater than 0 and sufficiently small, f of x bar plus lambda d is strictly less than f x bar. Now, for lambda sufficiently small, x bar plus lambda d is feasible to the original problem. So, this would imply that this contradicts that x bar is a local minimum. Because if I make lambda very small, I can bring x bar plus lambda d into the neighborhood, because x bar plus lambda d is already, I know it is feasible, and I can make lambda so small that x bar plus lambda d is in the neighborhood of x bar where that local minima holds. So, this contradicts that x bar is a local minimum. Is a local minimizer. So, this contradiction leads to the fact that this system, please note those who have looked at Fi might have questioned, but okay, this is a place where you can't question. So, just have a look at this, and so this system would not have a solution, and that is what we proved. Now, okay, if this system does not have a solution, what can we conclude? In order to conclude something, so if this system does not have a solution, something has a solution. So, if we get something which would have a solution, we can actually try to solve it and get our suspected suspected local minimizer. So, in order to do that, we will now state something called the Gordon's theorem of alternative or theorem of alternative, where basically there will be two systems of inequalities, and among those two systems only one would have a solution at a given time, in the sense that if one of them has a solution, the other wouldn't have a solution, and vice versa. If the other has a solution, if system 1 has a solution, system 2 has no solution. If system 2 has a solution, system 1 has no solution. So, Just let me write down. Now, let us look at what are the two systems. So, let F1, F2, Fm are convex functions on Rn, convex functions on Rn, finite value of course. Consider the system. We have studied a bit about convex sets and convex functions very earlier. So, we will just try to recall that, we will try to see what is there, how much we have done, and then we will try to recall that the notions of basic notions of convex sets and convex functions, and so that would help you in understanding this thing. Consider the two systems. And consider X to be a convex set in Rn. So, this is one system where I am expecting that if this system is solvable means there is an X in this convex set X for which all of these gives me a value strictly less than 0, or else if such a thing is not, this is one system and the second system is basically if this system does not have a solution, this will have a solution, that there would exist, this is a system of there would exist lambda element of Rm plus and lambda not a 0 vector such that this quantity is greater than or equal to 0 for all x in capital X. This is the Gordon's theorem of the alternative. It is called theorem of the alternative because the final statement is that both the systems cannot be simultaneously solved. So, that is the meaning of the word theorem of the alternative. Theorem of alternative means, I think people better usage is to say theorem of the alternative. Theorem of the alternative actually means that there are two systems here and at the same time you cannot solve the system. That is, if you find an x for which the system 1 is solved, you cannot find a lambda for which this will be true. That is, any lambda that you for which you say that this is true, that such a lambda must be equal to 0. This has a lot of interesting connotations in optimization, and we will use this fact to get what will be called as the Lagrange multiplier rule, because let us observe one fact. In our system, if what we have proved here, we have a chain of inequalities which does not have a solution. It is like our system 1 which does not have a solution. This is a function in D, another function in D, this is a linear function and these are affine functions, so they are convex functions. So here I will just take few minutes to actually make a little bit of recall of your ideas of convex sets and functions, because this is quite heavy stuff compared to what little stuff we had learned in the beginning. So then we can see how to first use this to get the John multiplier rule or the John free John necessary condition, and then try to give a brief sketch of how to prove this fact. So here we go back once again to recall what you have here, the definition of a convex set and a convex function. So that is fine, because you see convex set is a set who with all its points contains all the line segment joining any pair of points. So whenever there are 2 points x and y in C, the line segment joining them should also lie in C, and this is the definition of convex function, which for a nice looking convex function tells you that if you take 2 points on the graph and join it, if your function is from R to R, then you will have you will have the line above the graph, that chord. You see, we have studied a bit more about convexity. We have given a list of examples of which are convex functions. Here we have the famous quadratic function. Then what would happen if it is differentiable, and the fact that for a convex function every critical point is a global minimum, and then we came to line search method. That is enough for us to know. So, but let us first try to apply what is there into our thing before knowing how to prove it, because to prove this you would require a thing called separation theorem. So that proof, or how the proof would go about for that particular result, I will just give an outline, keeping again in view that of the broad nature of the audience, but still it will be quite mathematically involved. But mathematically involved does not mean that the word mathematically involved should not deter you, because it is very important to know that if you love mathematics, mathematics will love you back and help you in your work. So those who are doing other sciences and they have to use optimization, I mean most engineering sciences they have to use optimization, and you say that I want to shy away from mathematics, it is very strange, because if you go and make a search on the internet, a good number of mathematical optimizers are in engineering departments, and many of them had training in original training was in engineering, and then of course they did different things. So let us try to apply what is there. So we know what is a convex function, what is a convex set, and all these things. So what is very important, what important example of a convex set is a linear function. A linear function is, so a linear function is a function f(x) which is given in terms of the inner product. This is a simple linear algebra fact which you can prove if you know what is the basis of a vector space. So then this is a linear function. If you add something to it, for example if you say some other real number to it, then this becomes an affine function. So this is linear and this is affine, linear plus some stuff. So you can show that these two are convex functions. So in that sense, go back to this one, this is a linear function and this is a affine function. So basically what I am telling is that these two things does not have a solution. So now I want to apply the result there on the board to this thing, then what I would get? So I would get a vector. So if this system does not have a solution in D, here D is in Rn, so my x is in Rn, and x, capital X here is Rn. So there exists a lambda, a vector which should contain, we will put lambda naught for the thing corresponding to this, lambda naught, lambda 1, lambda 2 dot 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 lambda m, this is in R m plus 1 and lambda is not a 0 vector. So, you will observe that this is a very important conclusion, that this vector is not equal to 0, such that lambda naught into grad f x bar d plus summation I is equal to 1 to m lambda I grad g I x bar d plus g I x bar, this whole thing, that has to be greater than equal to 0 for all d in R n. Now, once this is true, you simply have the following fact. So, I combine a lot of things and which you can do this little homework yourself, which is a simple manipulation. Once you know this, set d is equal to 0 in particular. Hence, we would have so d is 0, so this is left, so this is greater than equal to 0. Now, as x bar is the solution, is a local minimum, it would imply that for all I g I x bar must be less than equal to 0 for all I from 1 to m, because x bar has to be a feasible set, feasible element, and because lambda i's are all greater than equal to 0, it is so it is an R m plus. So, here I forgot to put the plus, so it will be R m plus 1 plus. See, all of these quantities, that is lambda naught is greater than 0, lambda 1 is greater than 0 till lambda m is greater than equal to 0. That is the meaning of this in R m plus, R m plus 1 plus. So, what I should have is that summation lambda I should be less than 0, but then this we have greater than 0 from here. So, it implies that summation lambda I g I x bar is equal to 0. Now, since each of them lambda I g I x bar is a negative quantity, finally, we will get the following implication, that lambda I g I x bar is equal to 0 for all I. So, this implies now it says basically a linear function is greater than equal to 0 over the whole of R n, sorry not R m, R n. This is not possible unless the function itself is 0, this is a simple fact. So, if a d is greater than equal to 0 for all d element of R n, of course, a is element in R n also, otherwise you can't define inner product. this would imply that A is equal to 0. It is simply done by the fact that if you put instead of D, if you put minus A, because minus A is also in Rn, you will get this. So, what you will get is minus norm A square is greater than equal to 0, which will give you norm A square is less than equal to 0, but norm A square is actually greater than equal to 0. So, this would imply that norm A square is equal to 0, which will imply that norm A is equal to 0, which will imply that A is equal to 0. So, in the same logic that we would do, we can show now that. So, this would imply that lambda naught So, this would now allow us to summarize what is called the John necessary conditions or the John multiplier rule. If x bar is a local minimum for MP, just this John multiplier rule is usually used by some people just to make it look similar with what we call as the Lagrange multiplier rule, which was just for inequality constants, to which we will come in the next classes, and then we will combine both the equality and inequality. MP. Now, this math we will consider all our functions to be differentiable at the least. Could be continuously differential, could be twice continuously differentiable, but at least at the least differentiable with differentiable data. So, it is a inequality constant program. Then there exists lambda such that number 1 as I have told you explained you on the board in the last class, that this condition is called the complementary slackness condition, that both Gi and lambda I cannot hold with strict inequalities at the same time. If one is strict, the other has to be 0. Now comes the third and most crucial point. The point is this: this cannot be 0. This is the most crucial point, the central point of the result. So, what does this say? What does this fact say? What does this fact say? This fact and this fact combines. It says that if x bar is a local minima, then you must be sure of one thing, is a set of linearly dependent vectors. Now, one might get worried about the fact that what would happen if lambda naught is equal to 0. Of course, if lambda naught is equal to 0, then okay, f is not a part of the problem, then such a problem or such a multiplier is called an abnormal multiplier. So, this set of so called multipliers with the objective and constraints is called the John multipliers. See, the role of these multipliers is essentially to relate the coordinates, the components of the vector x. So, relate the components of the vector x so that you can actually find a solution. That is the whole idea of the multipliers at the end, when you just look at it from a computational perspective. So, this is called the set of John multipliers, and then if lambda naught is strictly greater than 0 or 1, we just, if lambda naught is strictly greater than 0 or just say lambda naught is 1, then because if lambda naught is greater than 0, we can divide by lambda naught and basically the same thing, the same story remains. Then we say that we have a normal multiplier, that is the good case. If lambda naught is equal to 0, we say that the multipliers are abnormal. Now, it is important to know at a given x bar, there can be more than one multipliers which will satisfy the condition. Once you know the x bar, then essentially what you have to find, what does the thing says, that okay, if x bar is a local minima, it has to satisfy this condition, means you have to find a lambda which satisfies this, this and this, okay, which satisfies this, this and this. Now, note this fact that even though I am getting, there could be a situation, there could be more than one multipliers which will satisfy this. So, I could get a set of multipliers where lambda naught is 0, and I could as well as possibly figure out a set of multipliers where lambda naught is 1 or strictly greater than 0. So, the problem MP is called regular. If at least one normal multiplier and if there are no normal multiplier, we call the problem irregular. Now, we shall show in the next class with examples that okay, there will be a problem whose Fridtjohn multiplier could be, there could be abnormal multiplier to that given solution, could be a normal multiplier. That could be a situation where there are no normal multipliers, and there could be a situation where there are only normal multipliers. But how do you assure that there is a normal multiplier? For that you have to impose certain conditions. One of the conditions which come out very simply from this is that okay, if this is 0, then in order to maintain 3, the lambda 1 to lambda m, this vector cannot be 0. So, which means the gradient of g I x bar is linearly dependent. So, if lambda naught is 0, these gradients of the constraints are linearly dependent. So, on the contrapositive statement is that if these gradients of the constraints are linearly independent, then we will never have lambda not equal to 0. So, that statement that the gradient of g I x bar are all linearly independent can be imposed on the constraints as a what is called as a constant qualification to get that I will never get a normal multiplier. Whenever if there exists a normal multiplier to this Fridtjohn inequality system, we said that the KKT condition holds, or the Karush-Kuntaker condition holds, because we have already spoken about the Karush-Kuntaker conditions, and we have spoken about the Kuhn and Tucker's work of 1951, and here you see, and then which is now can be viewed as a corollary to the Fridtjohn system, Fridtjohn or the John conditions. So, thank you very much. We will come with examples in the next class.